This is an example of a strong acid, strong base titration. In this titration, we're going to titrate 50 milliliters of 0.1 molar hydrochloric acid with 0.1 molar sodium hydroxide. Hydrochloric acid is a strong acid. This is going to be the analyte. Sodium hydroxide, of course, is a strong base. You can imagine that this 50 milliliters of analyte is in an Erlenmeyer flask, and that we have a burette filled with 0.1 molar sodium hydroxide. We can add different volumes of sodium hydroxide to the analyte, and we can calculate the pH at different points in the titration. So a typical titration problem will ask you to calculate the pH at various points in the titration according to the volumes of whatever it is that you're adding from your burette. In this case, we want to figure out the pH before we've started adding any sodium hydroxide, and then once we've added 10 milliliters, 30 milliliters, 49 milliliters, et cetera, et cetera, et cetera. So we can use the stoichiometry of the reaction to do these calculations. But before we do that, I want to just remind you guys of what's happening when we are combining a strong base with a strong acid. The net reaction, sorry, this is not an example. What I want to really write for you guys is a net reaction for what happens when we add a strong acid, which is, of course, the source of protons, to a strong base, which, of course, is the source of hydroxide. Those two are going to combine together to make water. And this strong acid, strong base reaction, of course, is also known as a neutralization reaction. So as we add hydroxide, it's going to consume the protons from the HCl to make water. And we want to figure out how the pH changes as this happens. So let's start off before we even start the titration. I like to set up titration calculations so I am tabulating these key values. First, I like to organize the volumes of sodium hydroxide that I'm adding. But I also like to keep track of the moles of protons at each point in the titration, as well as the total volume of the analyte at each point in the titration. Putting this over this and then taking the negative log will enable me to calculate the pH at various points in the titration. So before we add any sodium hydroxide, we're really just dealing with a strong acid problem. I have 0.1 molar hydrochloric acid, and if I have 0.1 molar hydrochloric acid, that's equivalent to saying that I have 0.1 molar protons. So the pH is just obtained by taking the negative log of that concentration. So before the titration starts, I have a pH of 1. And that should make sense because I have a strong acid. Now, I also want to fill in the number of moles of protons that I have at this point in the titration. And the reason I want to do that is because it's really going to help me in the next part of the problem. So to figure that out, I take the volume and I multiply it by the concentration of the HCl that I have. So 50 milliliters or 0.05 liters times that molar concentration tells me that I have 0.005 moles of protons to start out with. So that's the number of moles of protons that I'm starting out with. I have 50 milliliters, also known as 0.05 liters, as my total volume of analyte. Now, as I'm adding sodium hydroxide, my total volume should be going up. So 50 plus 10 is 60 milliliters, or 0.06 liters. 50 plus 30 is 80 milliliters, or 0.08 liters. 50 plus 49 is 0.099 liters, and so on and so on. So I can actually keep track of the total volumes of the analyte at different points in the titration. 50 plus 50, of course, is 100 milliliters, or 0.1 liters. 50 plus 51 is 101 milliliters. 50 plus 60 is 110 milliliters, and 50 plus 80 is 130 milliliters, or 0.13 liters. Those total volumes will make it easy to calculate the pH values down the line. Let's go to the second point in the titration where I've added 10 milliliters of the 0.1 molar sodium hydroxide. 10 milliliters, or 0.01 liters, multiplied by the concentration of sodium hydroxide, remember the problem told us it's 0.1 molar, tells us that I have added 0.001 moles of hydroxide at this point in the titration. Now, this hydroxide is going to react mole for mole with protons. So it will consume exactly 0.001 moles of protons. So if I subtract that from the original number of moles of protons that I started with, which was 0.005, I can see that I'm left with 0.004 moles of protons at this point in the titration. Going back to my table, I can insert that into my moles of protons column, and now I can take the number of moles of protons, put it over the total volume, and calculate the concentration of protons. 0.004 over the total volume gives me a molar concentration of 0.067 molar H+. Taking the negative log of that gives me a pH of 1.2, which I can add to my table. Now, going down to the next addition, once I've added 30 milliliters of sodium hydroxide, and again, this is 30 milliliters total of sodium hydroxide. If I multiply that by the concentration, that means that I have added 0.03 moles of hydroxide total. This is the total amount that I've added so far. So I need to take that value and subtract it from the amount of the number of moles of protons that I had originally. That tells me that I am left with 0.002 moles of protons at this point in the titration. So, putting that into my table, I know what I need to do. I need to put the number of moles of protons over the total volume and take the negative log of that. That is going to give me, let me put this in a different color so you can see it well. That is going to give me a molar concentration, and I can then take the negative log of it to figure out the pH. So this is the number of moles, and it's 80 milliliters, so I need that in liters. Taking the negative log of that will give me a value of 1.6 for the pH. So you can see that the pH is slowly going up. It's still acidic, because I still have strong acid, but it's less acidic than it was before.